So our first changemaker this evening is Marianna Uceda. Marianna is a fourth-year Ph.D. student in the Department of Mining and Materials Engineering under the supervision of Professor George Demopoulos in the Hydromet Lab. And Marianna is going to talk to us about how to build a greener battery. Marianna.
Energy is an invaluable resource. Access to energy has become fundamental for the promotion of human well-being and economic development. This is because we use energy in everything, from building our homes to powering our homes. Now, our current technology allows us to produce energy from a wide variety of sources, these being coal or gas, and this gives us a very large supply. However, this supply has an ever-growing demand placed on it. By who? Us. As of 2017, the Earth population has reached 7.6 billion people. It's doubled in 50 years. And alongside this growth, so has the demand for energy. So in the course of providing energy for this ever-growing population, we have to consider its environmental impact. And by that I mean its effect on the surrounding land, on people and wildlife population, and on the amount of pollution that it might emit. The most common types of energy sources are coal and gas. Now, these have a very high environmental impact, and this is because they produce large emissions that impacts the surrounding air and water bodies. Additionally, the mining for coal and drilling for gas heavily impacts the surrounding landscape. On the other end of the spectrum, we have wind power. It has a lower environmental impact because it produces significantly less pollutants. The problem with wind is that it poses a threat to some bird and bat species. The same thing can be said about solar power. It has a lower environmental impact, but some types of solar cells use some toxic heavy metals during the production stage. Now, another thing we have to consider in this graph is the degree of control that we have over power production and power delivery. You see, we can make energy from gas and coal plants during any time of the day and during most weather conditions, but we can't make solar power if there's no sun. And we can't make wind power if there's no wind. So we can say that we have a high degree of control over power production and power delivery of coal and gas plants. Now imagine that we wanted to be completely green and switch to only using solar cells as our power source. What will we do at night? You see, the electricity that is powering this presentation was generated moments ago and delivered just in time. The grid is the world's largest supply chain with zero inventory. If we want to switch to just using green energy like solar cells, we need to be able to meet the energy demand during all times of the day for our society to be sustained, or we can't even begin to think about getting rid of coal and gas. Right now, if we use just solar cells as our power source, our supply and demand balance looks like this. The demand is met during the day when we have sun, but it is severely lacking at night. Here, what we need is storage. And we can do this. We can use lithium-ion batteries. And they're already being used to store energy during high production times, like during the day, for use during low production times, like at night. Effectively, it's become the storage. It's restoring balance between the demand and supply and making the use of just solar cells viable. So if we go back to our control and environmental impact graph, and we take that solar cell and we couple it with a battery, we can improve the degree of control that we have over at least power delivery. And the same thing can be done with wind power. Now, lithium-ion batteries are also being used to power electric vehicles, as opposed to the conventional gas engines, which also produce a lot of pollutants. However, they're not just used to power cars or buildings. We're already using them in our phones. This shows that lithium-ion battery technology has wide versatility. Why? Because there's many different types, and these types are categorized based on the type of lithium-ion material that it is using. For example, this Nissan Leaf electric vehicle uses lithium manganese oxide, whereas the Samsung battery uses lithium nickel cobalt manganese oxide. So not only are lithium-ion batteries at the forefront of environmental efforts, they're already incorporated into our daily lives. So let me throw a curveball at you. What would you think if I told you that lithium-ion batteries aren't completely green? If lithium-ion batteries are going to be part of the clean energy solution, we need to be able to say that they're green from start to finish, from production to disposal. Otherwise, they're hypocritical. Now, to understand how lithium-ion batteries might not be green, let's first look at how lithium-ion batteries work. A typical lithium-ion battery cell is composed of two electrodes, the anode and the cathode. These two are separated by a porous membrane separator and submerged inside of a liquid that we call the electrolyte. This is completely sealed, and the two electrodes are connected by an outside circuit. And this circuit is then in turn connected to the load. Now, with lithium-ion batteries, the electrodes are composed of coatings on top of a metal surface. And this coating composition will vary depending on whether it's an anode or a cathode. Anodes are usually composed of carbon, and the cathode is usually the lithium-ion material. Now let's look at these coatings on a molecular level. The anode is composed of carbon atoms arranged in a honeycomb structure, and we have layers of it. The cathode is composed of lithium-ion layers and a matrix, and this matrix composition will vary depending on whether the type of material that we're using. Now, the lithium ions can be completely removed or reinserted depending on whether the battery is being charged or discharged. As it sits right now, the battery is charged, and that's why we find lithium ions in the anode. If we were to connect this circuit, we would cause a chemical reaction. This releases the lithium ions, and this in turn releases electrons. The electrons flow through the outer circuit and become electricity. The lithium ions flow through the porous membrane separator and towards the cathode, where they can become reinserted. If we then take the system and connect it to a power source, we can reverse the reaction and return the lithium ions so they can once again be stored in the anode. Effectively, we've recharged the battery for use again. Now, remember how I said that the electrodes are composed of coatings? Let's look at how we make a lithium-ion electrode coating. The first material we put in there is the lithium-ion material. Now, these materials tend to have really poor conductivity, so we can improve this by adding conductive material. And this is typically done by adding a small amount of carbon. We also add a binder to hold everything together. These powders are mixed with a liquid called NMP. This gives us a slurry, just like paint. And just like paint, we can then paint it onto a metal surface. This is the conventional fabrication technique for lithium-ion electrodes that we use in industry. However, the problem with this fabrication technique is twofold. The first is that NMP is toxic to human workers. Also, it is explosive. So companies have to take into consideration the type of equipment that they're going to use because they're scared that it's going to spark and start a fire. And I'm pretty sure everyone will agree alongside Samsung that we don't need any more fires associated with lithium-ion batteries. So you're probably sitting there wondering, well, then why do you use NMP? Well, that's because of the binder. The binder is highly specialized because it doesn't degrade during battery use. It's also very picky. It only wants to dissolve in NMP. And we need it to be able to dissolve in NMP so we can make a uniform coating among these three components. That actually brings us to the second reason why this conventional technique isn't very appropriate. You see, with battery materials, we use very small materials. They're nano-sized. And what happens when you put this in a slurry is that it becomes extremely viscous, and it doesn't want to flow right. This prevents it from being able to mix properly and create and makes non-homogeneous or non-uniform coatings. So this is where my research comes in. We are using a different technique to make our electrodes. We're effectively using a different brush to make the coatings. And this brush is called Electrophoretic Deposition, EPD. Now, EPD is a simple electrocoating technique that consists of submerging two metal surfaces inside of a liquid. And these surfaces are then connected to each other by an outside circuit. Now, within this liquid, we place the lithium-ion material, the conductive material, and in some cases, a binder. And we mix vigorously to make sure that we have a very well-mixed solution. Now, we actually call it a suspension at this point because there are powders in suspension. And in suspension, these powders develop a charge. And whether they're negative or positive depends on the material itself, and it also depends on the liquid that we're using. If we then take the metal surfaces and connect it to a power source, it forces a charge to also develop on these surfaces. As a consequence, the powders will migrate towards the oppositely charged surface and deposit. This gives us the painted layer that we then use as an electrode. Now, the key thing that we have to keep in mind when we're using EPD is we need a stable suspension. And by that, I mean that the particles will not agglomerate or stick together and sediment to the bottom. If we can meet this expectation, then the liquid can be anything from water to ethanol. And that brings us to the key advantage of EPD. It has the potential to be environmentally friendly. Now, within the McGill Hydromet group, we use this submersion setup hooked up to a power source to make our electrodes. This is a bit dirty, so let's look at a schematic I drew. And the submersion setup consists of an adjustable height bar that holds the two metal surfaces in place and connects it to a power source. So the way we make our coatings is we submerge the metal surfaces. And once it is submerged, we apply a voltage. And this is very brief. It's only done from anywhere between 5 to 15 seconds. This forces a coating to form. We can then remove the coating and allow it to dry and repeat this for as many times as necessary to create a thick enough coating. And this is what our coatings end up looking like. The back or gray part there is the aluminum foil that we submerged, and on top of it is the EPD coating that we just made. So I want to show you how these EPD coatings compare to the conventional coating technique. But to do that, we conducted some tests. And for the tests that I'm going to show, the EPD solution that we used was a mixture of water and acetonitrile. And the particles that we suspended that ultimately became the coating was lithium titanate, which was the lithium-ion material, carbon, which was the conductive material, and a water-soluble binder. So before we can test these out, we actually have to make a battery. So we take the coating and we remove a 1 centimeter disc and we assemble it into what we call a swage lock type cell. Now, this doesn't look like your regular AA battery, but it's what we use in the lab. And we can repeat this process for a conventionally made electrode. So we have a battery that has a conventional electrode, and we have a battery that has an EPD electrode. So now we can compare its performance. We can do that by charging, discharging, just like you would with your phones. If we do that, we can measure the battery capacity, and that is the amount of charge that is stored within 1 gram of the material. This value varies depending on the type of material that you're using. But for lithium titanate, that is what we used, the theoretical capacity is 175 milliamp hour per gram. Now, this is actually quite low, but we have an advantage with lithium titanate, and it's that we can deliver that power, that capacity very fast. We can also charge it really fast, and you want to be able to charge your phones fast, but you want to be able to deliver power fast when you're using something like a power tool that needs fast power delivery. So now, we're going to take this battery and charge for 5 hours and discharge for another 5 hours. So one cycle of charge and discharge takes a total of 10 hours. And for the EPD electrode, what we find is that we reach the 175. And there's a gradual decrease. This is expected in a lab setting. When we look at the conventional, we find that it's much lower. It doesn't reach the 175, but it's at an equal degree of degradation. So let's make it faster. Let's take 1 hour to charge and 1 hour to discharge. We see no difference. So let's speed it up even more. 30 minutes, 6 minutes, 3 minutes. Now we're really seeing a difference between the EPD and the conventional electrode. At 3 minutes, the conventional electrode capacity doesn't reach half of what the EPD does. So we can say that the EPD electrode performs better in fast rates. That's great. But now we need to know why. And the difference between these two was the way that we made the electrodes. So we took these electrodes, or the coatings, we cut them in half, and we imaged the cross-section. So up here, I have an image of a scanning electron microscope image of the cross-section of the conventional coating along the thickness. And the first thing you might notice is this chunk in the middle. What is it? You see, we have 3 different types of materials, right? We have the lithium titanate, we have a carbon, and we have a binder. So how can we know what this is? With the scanning electron microscope, we can use a technique called electron dispersion spectroscopy, where we can map out elements. Lithium titanate is the only material that has titanium in it. So if we then make a titanium map, we can see where the lithium titanate is spread out. And that's just what we did. So we found out that this gray agglomeration or chunk in the middle is lithium titanate, with the carbon and the binder spread around. Now, if we compare what this looks like with the EPD electrode and its corresponding titanium map, we see a huge difference, right? With EPD, we can say we have a more uniform coating. Now, if you remember what I said earlier, the conventional fabrication technique doesn't make very uniform electrodes, and now we can visually see that. So we can say, so far, that EPD produces very uniform electrodes that perform really well at fast rate. But what is the connection between the uniformity and the rate performance? Well, we measured the conductivity of both of these electrodes, and we found that the EPD electrode was 15 times more conductive. So let's look at a schematic of these coatings. Here we have the lithium titanate in gray with the carbon in black. Remember how I said that the carbon acts as it improves the conductivity of the overall material? It sort of acts as like a highway for the lithium ions and the electrons to flow through. For this material to perform, the lithium ions and the electrons have to reach the surface of the lithium titanate to react. And when lithium titanate is in contact with carbon, this happens very fast. But what about this middle lithium titanate? Effectively, this is like having a landlocked house that has no access to road. The lithium ion and the electrons can still reach it, but it's a lot slower when it has to flow through the lithium ions. So we don't have this problem with EPD because we have well-dispersed carbon roads and no landlocked lithium titanate. So now we can say three things. EPD produces uniform electrodes. This improves the conductivity of the overall electrode, and this ends with a better performance as a battery. Now, if you remember earlier, we were talking about combining lithium-ion batteries with solar cells. If we do this, then conductivity is a big deal, because low conductivity means high resistance. And when you have high resistance, you're losing energy as heat. And this means a low overall efficiency between your solar and your battery couple. But we don't have this problem with EPD electrodes. We have higher conductivity, so comparatively less energy is lost as heat. This means that our overall couple has a higher efficiency. So not only are we making lithium-ion batteries that perform great, they're greener, and now they have better efficiency. But you're probably thinking, well, you made those in a beaker, in a small glass jar. Can this really translate into industry? And yes, it can. I know this because it's already been done. The EPD has been scaled up. It's currently being used as e-ink or e-technology. And this is used to coat corrosion protective layers on top of car bodies. And this looks like this. We have a big tank, which is effectively my big beaker. And inside we have the coat or the paint that we want to paint on top of the car bodies. The car bodies are submerged. They're held by a rack and submerged inside of the tank. And a voltage is applied. And this forces a protective layer to form on top of it. And the advantage that this coating technique might have over the conventional direct spraying is that the rack itself that is holding the car body, if that's insulated, then nothing is going to deposit on it. So we have no overspray problem. We have no loss of material. And this same advantage can be translated to making lithium-ion electrodes. So in conclusion, I can say that electrophoretic deposition is a potentially environmentally safe electrode coating technique. Additionally, it makes electrodes that have excellent battery performance. And we know that this can be scaled up because it's already been done. So we can meet the energy demand and be green from start to finish. Thank you very much. Oh, yeah, that's I forgot.
Thank you, Marianna. If we have time for one or two questions. Jan?
Obvious question, do we have enough lithium in the world to actually do this nice thing?
That's difficult to say. To be honest, my specialty isn't knowing how much lithium we might have at our disposal, but right now, actually, I'm not sure.
That might be a big point, but we have several maybe.
Well, we do have That's my advisor.
Well, in response to Jan, actually we have, and also we can just replace it with other elements like sodium, for example.
Oh, that's very true. Yes.
So I have another question if you have time.
Yes, sure. Maybe use the microphone, please.
I guess I'm well enough, so I
Just for the video, yeah, please, yeah.
So, I forgot my question actually.
That's okay. You can ask me afterwards if you'd like.
Oh yeah, you talked about the scalability, but how about the flexibility of your system? You know, you are working on titanate metrics, but how about other metrics like, let's say, iron phosphate metrics?
Well, that's a really good question, thank you. And yes, it's quite flexible. It all depends, like I said, if we can make a stable suspension. And in most cases we can. I've worked with a variety of different materials, lithium iron silicates, lithium cobalt phosphates, and I found that yes, I've been able to make a good coating. I've never actually tested it further as a battery, but depending on, if you can just make a stable suspension, you can use EPD.
Okay, maybe one more question.
I wonder if you could draw an analogy to supercapacitors and what's used to create them, which are now being used as a supplementary source of instant power, even in cars.
I'm not sure I know enough about supercapacitors to be able to make an analogy. So sorry.
Maybe one last question then, sure. Well,
Ultracapacitors power density is about 1/200th of lithium-ion right now, the commercial, just to answer that question. You referenced charge rates for the reference cell or the traditional cell, a decay of, it looked on your graph, something like half of the capacity by 30 cycles. Commercial
Yes.
lithium-ion, typically for cars, is 80% over 1,000 charge cycles at 1C. Have you extended that test over time, over thousands of cycles, and seen what it looks like?
We haven't extended past 1,000 cycles. I've only made it up to 150. When I took 1 hour to charge and 1 hour to discharge, it went well into the 150 cycles with only less than 9% capacity loss.
great, okay, well, thank you, Marianna.
Thank you.
Take our speaker.